For almost 500 million years, sharks have been residents of our planet and sat at the top of the food chain. Throughout their history, sharks have evolved and adapted into some of the most efficient predators on our planet. But what are the unique and specialized traits that have turned sharks into such impressive hunters? While regenerative teeth and cartilage skeletons contribute to sharks' unique morphology, arguably their most interesting feature is their sensory ability called electroreception. Similar to how some mammals, namely bats, dolphins, and whales, sense their surroundings and communicate with sound waves, sharks, as well as other elasmobranchs, like rays and skates, use the electric signatures generated by living creatures to hunt and defend themselves. In the process of echolocation, for instance, a bat could locate, track, and catch a fly in complete darkness, simply by how sound waves created by the bat bounce off the fly and back to the bat. In spite of the precision of echolocation, it pales in comparison to electroreception. When a shark locates prey, the electric signatures created by the prey's neurons alert the shark as to where the prey is, regardless of how quickly it's moving, how visible it is, or even if it is concealed by reef rock or buried in the sand. Electroreception transcends the need for light, any physical barriers, and even all of the shark's other senses. Even when there is no light, no scent, or no other indication of food, a shark can hunt in certainty, based on electroreception. In a demonstration, we can see sound waves being sent from a dolphin and electric signatures being received by a shark. Imagine a wall in front of both the dolphin and the shark. If the dolphin were to try to locate a fish behind the wall would reflect the sound waves, and no information would be gathered by the dolphin as to where there is a fish or not. However, if a shark were to do the same, in spite of the wall, a small fish could not only be detected, but the shark could even determine which direction the fish is moving in. A shark's ability of electroreception is so refined that if a AA battery were to be hooked to a wire hung from the Florida coast in New York, a shark anywhere along at any point on the coast would be able to detect the current. These abilities began as elasmobranchs evolved from a previous ancestor, approximately 450 million years ago, nearly 100 million years before trees came into existence. Electroreception was first theorized 300 years ago by an Italian doctor and taxonomist called Stefano Lorenzini. Despite being a physician, Lorenzini had a great interest in anatomy and taxonomy. While dissecting a saltwater stingray, Lorenzini found small, black pores that dotted the nose and face of the ray, the same pores seen on the snouts of sharks and skates as well. These small pores led to tubes full of a clear, viscous gel, which led to a small pouch close to the brain. This pouch, to Lorenzini, resembled an ancient Roman vase called an ampullae. Being the first to discover this new sensory organ, he named the structures the ampullae of Lorenzini. With the first discovery of electroreception being uncovered, major developments will not be made until much more recently, approximately 60 years ago, during many studies conducted through the 1960s to the 1970s. In studies in particular conducted in 1966 by Dr. Mathis Kalmajan, the structure and function of the ampullae of Lorenzini is clearly explained. The pore itself is highly positively charged, making it incredibly sensitive to electric signatures, and the gel within the chamber highly conductive. At the end of the chamber, in the ampullae-like pouch, a nerve connects to the brain, very similarly to an octave nerve in an eye. Now, with an understanding of the organ's structure and function, Studies conducted by Dr. Stephen Kaijura at Florida Atlantic University allowed experiments with sharks and their ability of electroreception. In their experiments, they took wild sandbar sharks from the coast of Florida and used a dipole to deceive them into thinking it was food by replicating the electric signatures produced by their prey. After every trial, the sharks would always exhibit a predatory response and show interest in the dipole, successfully proving that a shark's sense of electroreception will convince them to hunt false prey. After learning of the history of Lorenzini, Kalmagin, and Kaijura, and having my own interests and aspirations with sharks and electroreception, I became eager to see if this could be replicated in project-based science. I reached out to the current expert in the field, Dr. Kaijura, to find out how practical his work was, or would be, when demonstrated in the confines of a classroom and a fish tank. Good morning, Dr. Kaijura. My name is Connor McKeegan, and I'm a senior at East Kentwood High School in Kentwood, Michigan. As a senior student who is enamored with marine sciences and elasmobranchology, I jumped at the opportunity to join a class called Project-Based Science, where students can propose research projects, and with the approval of our instructor, Mr. Carl Warfield, can pursue them for the entire school year. I pitched my project idea on the second day of school to demonstrate an elasmobranch's ability to detect an electric current created by living animals by using a freshwater stingray and a dipole. What this is cultivated into is an agreement with my instructor to obtain a spacious saltwater tank, a saltwater elasmobranch, as well as the electrical equipment necessary to imitate the electrical signals produced by a potential prey item. Needless to say, I am absolutely ecstatic. Earlier this week, I read a 2017 dissertation by one of your graduate students, Kyle C. Newton, which references experiments of the same principle as my own, as well as in this article attached. I email you today to ask for your guidance. What electrical equipment would be ideal for replicating a neuron signature? Any advice or guidance you can offer would be incredibly appreciated. Thank you, Doctor. Regards, Connor McKeegan. Dear Connor, congratulations on getting resources to do your project. To simulate the electric field of a prey item is actually very simple. Take a look at the attached paper, which includes a circuit diagram for the stimulator. You only really need a 9-volt battery, a 1 mega ohm resistor, and an on-off switch to make a simplified version. This will cost you no more than $10. Adding an ammeter in series will allow you to know the applied current in your setup. The meter needs to be able to read down in the microamp range. There are several publications on using this same technique on my website below. After you have placed all your electrodes on the bottom of the tank, buried is best, but under a plastic plate or a screen window is fine. Use some food or food odor to stimulate the animals to start to search for food. Then, activate the electrodes and film the response so the shark or ray initiates a turn towards the dipole. Now that I had received confidence that this project could be replicated in a classroom environment, I began to draft initial ideas for both the elasmobranch we could house and the equipment we could use to test it. While my initial proposal involved a freshwater stingray, we quickly moved to a saltwater preference, as a 180-gallon saltwater tank was available. We began to look at our marine options. Firstly, California blue spot stingrays were proposed. They grow to the size of dinner plates, are community compatible, and would be electroreceptive, as they are elasmobranchs like sharks. We decided against them for availability reasons. We also considered epaulet and horn sharks, but for both size and cost reasons, we did not end up deciding with. Our determination fell onto cat shark pups. Cat sharks, also known as bamboo sharks, are called cat sharks because of the barbels around their snout. They were discovered in 1830 by a zoologist named Edward Bennett in coastal northern Australia. Cat sharks are very slender and have protective eyelids to prevent damage from light during the day. They are lazy, opportunistic hunters that often wait for prey to come along. They will eat any crustacean, small fish, or mollusk they find, and tend to have timid personalities. To house our sharks properly, we wanted at least 5 times the length of their bodies for the length of our tank. Because it was a 60-inch tank, and Oni, our largest cat shark, was only 6 inches, we satisfy this rule easily. However, these sharks will get larger in life, growing to approximately 5 feet themselves. Sharks, cat sharks included, are sexually dimorphic, which means the females tend to grow larger than the males. Assuming this, we can both expect both female shark pups to grow well past 50 inches. Cat sharks require specific water parameters, especially if they are younger and more vulnerable. The pH of the water must be kept between 8.0 and 8.4. The specific gravity, or salt concentration, in the water must be maintained between 1.020 and 1.025. Tank temperatures can range between 72.5 to 82.5 degrees Fahrenheit. One important consideration must be made into our sharks' treatment and care. Metals should be introduced to the tank as little as possible. And trace metals, naturally found in seawater, are extremely small amounts of iron, copper, nickel, and other metals. They exist and perform for very specific and niche functions for the various underwater cycles. But when they exist in a higher concentration than their already tiny amounts, they can wreak havoc on entire ecosystems. Copper is especially detrimental to sharks and proves to be incredibly toxic. When a shark is exposed to high enough concentrations of copper, it begins to attack both the respiratory system and the nervous system. As sharks breathe water through their gills, high concentrations of copper in the water will inflame and cause infections in the gills, which can be highly fatal. Furthermore, copper also serves to disrupt electroreception, as well as many other senses that the shark possesses. The ability to hunt or eat becomes very diminished by this, and can cause a shark to not eat and become lethargic. This symptom is just as fatal, but occurs slower. Because of these risks, we only use plastic tools when both feeding or experimenting with our sharks. Our cat sharks, especially as pups, must maintain a voracious feeding cycle to get the right amount of calories and nutrients to grow at the rate that they should. Because of this, our cat sharks are eating approximately 1 ounce of seafood a day, which is quite large in comparison to themselves. Cat sharks prefer squid and minnows most of all. In our feeding process, we start by putting frozen cubes of fish and squid into a microwave-safe cup filled with tank water. We then microwave the frozen food until thawed in hot water. We mix and add to the tank. This is a typical feeding response. These animals are nocturnal and do not prefer bright overhead lights. Optimally, they hunt in subbright, warm water, where there is rock to maneuver between and hide within. In the setup of our tank, we achieve both open space and concealment behind live rock. Our tank was designed to facilitate the demonstration of electroreception in the most ideal circumstances. It was now time to plan out the materials we would use for the device. A total of 7 components were necessary to imitating such a low voltage. We would need wire, thin enough to conduct such a weak current, resistors to weaken the current, a battery to provide the current, adapters to connect the battery to the wire, a capsule to contain the dipole, sealant to prevent water from disrupting the device, and an ammeter to check to see if the current is as low as it should be. I found most of my items on Amazon, but a few I either found in person in department stores or in the materials we had at school. Firstly, I found these resistors. They provided a resistance of 10 megaohms, which would turn the 9 volts of energy into 20 millivolts. If a second resistor were to be ran in the current, the combined resistance would register around 7 millivolts. The only wire able to conduct such a small signature is the 30-gauge stereo wire, which has a diameter of 1/100th of an inch. Comparatively, a human nerve still has 1/100th the size of that. Regardless, this wire would work. I used these cups to seal the dipole within. They were waterproof entirely, and were made of a pliable plastic, so fitting the dipole within was easier. The sealant was used to prevent any water from entering where holes had been drilled into the capsule. A Duracell 9-volt battery was used to power the dipole, and was connected to the wire using these alligator clips. The voltmeter was added in series after the resistors to measure the voltage applied to the dipole. Here's a diagram of the dipole used in Dr. Kaijura's experiments. In the top left, we see the external power supply, which is located away from the water. Similarly to our design, a 9-volt battery is being used to power the dipole. The circuit is led through an on and off switch, and then to a high and low switch, to determine the strength of the current going through. One resistor will resist the current from 9 volts to 20 millivolts. Adding another resistor will decrease it further to 7 millivolts. While our design in our experiment does account for a high and a low voltage setting, we can only control the device being on or off from the battery connection itself, and do not have a switch for it. Past the resistors, an ammeter is added in series to read the resisted voltage. In their design, a choice between 4 different electrode plates is present, and in ours, it is only set to one singular capsule. We are now about to see our dipole perform in our first demonstration. For this demonstration, the dipole was situated between the aquarium glass and the rock. The salinity of the tank is 1.022, the water is 80 degrees Fahrenheit, and the pH of the tank is 8.2. Both sharks have not eaten in approximately 24 hours. As the video begins, the dipole turns on, pulling the attentions of both sharks. In the video, we see both sharks swim for the area of and around the dipole after it turns on. These turns and behaviors for sharks demonstrate a predatory response. We can see that dipoles are successful when tasked with attracting sharks. We are about to see our dipole perform again for the second demonstration of electroreception. For the demonstration, the dipole is still situated between the aquarium glass and the rock. The salinity of the tank is 1.022, the water is 80 degrees Fahrenheit, and the pH is 8.2. Both sharks have not eaten in approximately 24 hours. Contrary to the first demonstration, the dipole has been set to low, and instead of 20 millivolts being conducted, currently it is 7. Interestingly, only one of our sharks seems to detect this signature of the dipole, but her response is far more attuned than before, even when the current was higher. Instead, we see her swim to the dipole, overshoot, seem to stop descents, and then readjust directly under the dipole. I postulate that 7 millivolts is a more convincing signature, but a more obscure one. This would explain the heightened response from the one shark that did respond, and the other shark's complete unawareness. The implementation of this experiment was by no means perfect. Performing in a classroom surrounds the sharks with live wires and devices, which greatly impact the electromagnetic field around us and that the sharks use to hunt. Because of this, if the demonstration were performed in a different location, there could be less distraction for the sharks to be affected by. Furthermore, using older and more mature sharks, or sharks that have experienced live feeding all their lives, could prove more beneficial. With these two ideas in mind, we can assume the best place to perform this experiment would be in the open ocean with wild sharks. Why do this? Why does electroreception, or how sharks sense the world, matter? Sharks serve a role as keystone species in almost every environment they live in. When determining the health of a coral reef, for instance, the presence of sharks is a clear indicator of a healthy, populated ecosystem. When shark populations drop, the entire balance of the food chain is thrown into chaos. Important feeder species, like krill, silverside, sardines, and mackerel, are all overeaten, as there are not enough sharks to regulate those species' predators, like tuna, cod, albacore, and many other oceanic tertiary fish. Sharks are constantly victims of pollution and bycatch, where often they die, mangled in fishing nets not even meant for them. The regulation of the world's largest ecosystem falls directly onto sharks, and therefore, to protect our oceans, we must protect them as well. Now, imagine using devices to lure sharks away from fishing nets, or stingrays away from crowded beaches. Imagine using devices like our own to herd sharks into protected, conserved waters. People greatly underestimate the power of controlling the movement of an entire species and the potential conservation capabilities. Currently, our planet is faced by near insurmountable atmospheric and oceanic pollution. The ocean itself filters approximately half of the world's carbon dioxide, and when the ocean is diseased, like it is now, the carbon it is responsible for replacing stays and chokes the earth. It is believed that only 10% of large ocean fish remain. Of the over 600 known species of shark, over half are endangered and a third are insufficiently studied to properly approximate their populations. Sharks, and all they do to stabilize and clean the oceans, are one of the most threatened species of any. So what can be done? Understanding the issues the oceans face is paramount. Dive into issues further than what we discussed here, including oceanic acidification, the microplastic pandemic, and coral bleaching. Understanding the roots of these issues will better direct your activism. Next, consider donations to corporations and funds to clean and preserve the ocean and its many unique habitats. On a small scale even, an impact can be made through sharing information on social media or by watching shows and media that give proceeds to oceanic conservation. We share this world, not only with each other, but with every other organic life present on our planet. It is each and every one of our individual responsibilities to take care of the residents of the only planet we know.